Okay, let's go ahead and get started. We're going to be on the pad for most of the day, but we'll start out on the computer. We had a question of the day about savory versus sweet, so there's the results for that. But as I said, we're going to be switching to the document camera for most of today. So the topic that we're going to be talking about today is not something that you'll be practicing on the homework. I mentioned that we're going to do a third linked list section tomorrow to practice that, and we'll start some new material on Wednesday that we'll discuss in Thursday's section and then in Friday's lecture as well that will be relevant to the fourth homework assignment. But we have a bit of a break here so we can fit in an extra topic. And so today's topic, one of the things that I'd say about 143 is that what we're trying to accomplish in the course is to kind of teach you the best of computer science, some of kind of the best ideas that are out there in computer science. But another thing that we're trying to accomplish is to kind of teach you the best of object-oriented programming. And it's hard to do both of these things, especially when you're on a 10-week quarter system. So we don't quite do justice to either of these things, but we do a pretty good job, I think. And so today I'm going to be talking about a best of computer science topic. So this is a topic that in the olden days, in the traditional course, before we had so much object-oriented programming material to cover, this would have been something that we might have spent 2 or 3 lectures on and might have had an exam question about. We can't afford that in the kind of the current version of it, so we talk more about the idea here. The general topic, I would say, has to do with efficiency, thinking about efficiency. And I almost don't want to talk about efficiency, partly because I feel like a lot of novices and even people who haven't programmed, they're young, but they think they know a lot about programming. There's kind of an obsession with efficiency, and what seems to me to be an unhealthy obsession with efficiency. There's a famous quote that premature optimization is the root of all evil. I've generally heard it attributed to Don Knuth, but apparently Knuth said that Tony Hoare said this, the guy who invented Quicksort, and Tony Hoare said that Don Knuth invented this. So anyway, they can't make up their mind about who came up with the quote about the premature optimization. But in any event, they both seem to agree that that's not a good thing. Now, it didn't say that optimization is the root of all evil. It said that premature optimization is the root of all evil. So the idea would be, don't worry about efficiency initially. Worry more about correctness, getting things right. But obviously, we do care about efficiency. So ultimately, you may look at this and try to figure out where are there bottlenecks, where can I improve the efficiency of a program. But wait until you have a working program would be the recommendation, of Knuth and Tony Hoare. I guess maybe an analogy I would use for this would be, if you've got some jet airplane and you find that it's too heavy, you're concerned that this thing is not going to be safe to fly, and so when you have the unhealthy obsession with efficiency, it's kind of like you say, well, let's put the pilot on a diet, And I guess, technically speaking, if you can kind of get to the pilot and make sure the pilot doesn't have those extra jelly donuts or something, well, sure, that slightly changes the weight of the plane. But obviously, it's not going to fix the problem. So the idea would be to focus on those areas where they could really make a difference, instead of something like trying to put the pilot on a diet. The technical term that we use for what we're going to be talking about today is complexity. And that's a little misleading because it kind of sounds like, if you had code that was hard to understand, Linked list code can be very detailed and very complex in that sense, in that you have to draw pictures to understand why are all these different things happening with this code. But that's not what we mean, computer scientists mean, when we talk about complexity. What we're thinking of is a measure of the resources that are required for a given algorithm or a given program to execute. And there's lots of different resources that a program can require. Two of the most common are time. So, how long does it take this algorithm to run? And space. How much memory does it take to run this particular algorithm? These are the two that probably people worry about the most. And there's an interesting relationship between the two, in that if you're willing to devote more space, you can generally have it run faster. Or if you have very limited space, you can often still solve the problem, but it might take longer to run. So there's often a trade-off here between time constraints and space constraints. When computer scientists talk about the complexity, we tend to kind of obsess about time. So we tend to be thinking about how much time does it take for this thing to execute. So this is an area where, so our field is known as computer science. And I've heard the famous computer scientist named Jeff Ullman. I remember one of the things he liked to say is that anything that claims to be a science is not. Our field, it's hard to quite say what our field is. It has some engineering aspects to it. It has some mathematical aspects to it. It has some science aspects to it. It's a little hard to characterize. But anyway, Jeff was making a joke. Jeff just won the Turing Award a couple of weeks ago. That was announced. But in any event, what we're going to be talking about today is actually an area in which we as computer scientists are acting a little bit like actual scientists. So what we're going to want to do is to have a model that predicts things that you can observe and measure. So for example, time. That if you had some kind of a model that predicted how much time an algorithm was going to take, then we could actually go and run experiments, collect some data, and see how good our predictions are. So, and I'm going to give you a model. I'm actually going to do that with you in a minute. So this is a way in which we are somewhat like computer scientists. There's a notation that we use for this, what's known as big O notation. It's a way of kind of describing different categories of algorithms. I'm going to show you in a minute that we kind of like the idea of thinking that there are different families of algorithms that have different complexity to them. Well, let's think about a specific example. So index of was a method that we wrote for both the array int list class and the linked int list class. And it's an example of what an algorithm that we would call linear search. So we've seen actual code, but it's also, a well-known algorithm to search in a linear manner, to search, from beginning to end through a sequence of values and see if something is there. Well, how much work does the index of take? It was a for loop, the way that we wrote it in the array code. It was a while loop, if I'm not mistaken, in the way that we wrote it for the linked int list class. But basically, what we do is we start at the beginning and see if that's what we're looking for, and if not, we go to the next one, go to the next one, go to the next one, go to the next one. The array case is the simplest one to think of. You just kind of go, look at index 0, index 1, index 2, index 3. Maybe you get lucky and you find it very early in the array, so it might be that it's super fast and you find it right away. If it doesn't appear at all, so if it's a failed search, you have to look at all of the different things that are in the structure. So for this big O notation, we think in terms of n, where n is some measure of the input size. And so for something like an array int list, n would be how many things are in the list. That's, if there's 1,000 things in the list, it's going to take a different amount of time than if there's 1,000,000 things in the list. And if you called index of on an array int list, that had 1,000,000 things, and if the value's not there, it's going to have to look at all 1,000,000 of them to determine that it's not there. So it might look at all n of them. So it might be a small number, might be a large number. If there's one occurrence of the value in the list, then on average you'd find it about halfway through. In any event, you can think of it in these various ways. We would conclude that this is an O of n algorithm. So that's a big O. That's where that terminology comes from. And we have a function inside of here that's meant to kind of characterize the amount of whatever resource we're talking about. So if we're talking about time, as we are in this case, a function that would kind of indicate how the time changes with the input size. So by saying that it's O of n, I'm basically kind of saying that if I were to graph it, so suppose I were to graph the time versus the input size, and I ran an experiment, I would expect to see a line. That I expect that the time is related to n. There can be lots of different functions in here, n squared, n cubed, log n, all sorts of different kinds of things that we could imagine would be there. Well, so imagine, for example, that we had an O of n algorithm versus an O of n squared algorithm versus an O of n cubed algorithm. And we were going to be, actually I wanted to kind of draw that across instead of down. Let me do that on the next piece of paper. So I kind of had in mind that those were my columns, O of n squared, and O of n cubed. And so if for different input sizes, if there were n things that I was going to work with, we'd think that if this is predicting the time, somehow there would be, something on the order of n here, n squared, n cubed. This first row is not the row that we care about because we're not predicting the actual time. You'd need some kind of a constant thrown in there that would try to predict the actual time. So these are not kind of the important numbers. What we care about is what happens as the input size changes. So if the input size is n, then we would kind of say that this is how much time we would predict it takes. Suppose that the input size is doubled, so that we had 2n. So what do you get when you plug 2n into these different functions? What you get here is 2n. Here you get 2n plugged into n squared. So 2n quantity squared is going to give you 4n squared, because that 2 gets squared when it's included in that function. And for the n cubed, we would have 2n cubed, which gives us 8n cubed. So what we really care about is the kind of the growth rate. We're interested in how does this change as n changes. So this is a doubling in the input size, and we would say that for a linear algorithm, there'd be a doubling in the amount of time. That would be our prediction. We'd be predicting that the time for an n squared algorithm would increase by a factor of 4 when you double the input size, and that for an n cubed, it would increase by a factor of 8. Because we're thinking of ratios here. That's why I say kind of the initial numbers here are not as important as understanding these multipliers, kind of how things change as we increase the size of the input. And if we had triple the input, 3n, for linear we would think that takes 3n time. For n squared it would be 3n quantity squared, which is 9 squared. And then for cubed it would be 3n quantity cubed, which would be 27n cubed. So the prediction here is that if you triple the size of the input, for an O of n algorithm, it would triple the time. For an O of n squared algorithm, it would increase the time by a factor of 9. For an n cubed algorithm, it would increase the time by a factor of 27. So we are trying to characterize the growth rate. Another way of thinking of it is that if we had, say, we took this O of n algorithm and we plotted for different sizes of input the different times that we get, we're predicting a line. We're predicting that it's linear. Here, what we're predicting is that the curve is an n squared curve. Here, we're predicting an n cubed curve. So we're trying to kind of predict how that changes as the input size grows. That's the kind of thing that we're interested in thinking about. And in a few minutes, we're going to be going over a problem where we're going to see an O of n, an O of n squared, and an O of n cubed solution to that problem. And I'm going to show you a program at the very end that I run that actually times this thing, times the different algorithms, the starting time and the ending time, and it computes these ratios. So it's going to kind of tell us whether our predictions are good. So whether the doubling leads to 2, 4, 8, whether the tripling leads to 3, 9, 27. That'll be data that our program will give us. And again, we're trying to be a little bit like a scientist here by having some kind of a model that would predict this. Let me mention something that I would hope is an instinct you've kind of developed from thinking about limits. That if you had something like 0.002 n cubed plus 65,000 n squared plus 6n minus 4, if you had something like this, in the limit case, they tend to have this divided by some other polynomial involving n, and they ask you what's the limit as n approaches infinity of this ratio of two different things. And so you guys, if you've done that in calculus, you would kind of develop the intuition that if we're thinking of extremely large values of n, as n is approaching infinity, then of course a minus 4 doesn't matter. And when you're dealing with, an n that's gigantic, then 6n, versus something like an n squared or an n cubed, the n term just is not meaningful compared to the others because the other terms are getting so much bigger. And you might see that that's a small constant and that's a big constant, but eventually the fact that this is an n cubed and this is an n squared, the n is going to dominate as n gets bigger and bigger and bigger. So we don't care about the n squared term either, even if it has a high multiplier like that, because eventually n gets big enough that it's the n cubed that kind of dominates. And then we're not really coming up with precise predictions about time. So we don't care about things like this constant. What we care about is n cubed. That's the dominant term. That's what we want to pull out of all of this. And that's what we would say, if this was an equation that was predicting somehow the amount of time, we would describe that as an O of n cubed algorithm. We care about the dominant term. We exclude the other terms. Let me mention, I should have said this, but the big O does have a formal definition to it. And if we were spending 2 or 3 days on this, I would tell you the definition and we would work with it. But we're kind of doing an informal version of this. So I'm basically not going to try to define big O. I'm trying to give you an intuition about big O. One of the intuitions I've always had is I always think of O as being short for order. It's telling you kind of the order of this, of what order, of what magnitude, is the way that we're thinking of it. But again, so I'm trying to give you an informal sense of it. It's meant to predict things like, in this case, the time and how the time varies as we change the input size with different, doubling and tripling, for example. Okay, so I wanted to mention, what else did I want to mention? Okay, yeah. Well, let me talk about this. Oh, one of the things that I did want to talk about is I wanted to talk about the idea. Oh, hey, sorry. I was trying to figure out what I wanted to talk about next, and I was a little confused. I haven't given you my model, so I haven't told you kind of how I would do this kind of prediction. So let me give you a model and basically say that the count of the most frequently executed executed line of code is the big O. You know, that's basically that so there's lots of lines of code, you know, that are potentially being executed. And if you find that line of code that's executed the most often, and you have a formula for how many times that line of code is executed, that provides you the big O. That kind of gives you the big O. Now, it's not quite true. There are some exceptions that I wanted to mention, but it's a pretty good predictor. I mean, so the idea would be that if you take some program and you run it, and you do something like the following. So as a line of code gets executed, you make a little bit more gray in its background. You know, and if we come back around, if we say execute that line of code, darken it a little bit more. And if we hit that line of code a third time, darken it even more. So the idea would be to kind of turn your program on and let it run, you know, let it run for a while, and then stop it, and then look at the lines of code and find the charcoal black line of code, the one that has the highest count, the one that's executed the most often. There are tools that help you to do this. There's a tool known as a profiler that will give you counts of lines of code. So you could get a profiler to actually figure this out, to find the line of code that's executed most often. Now, I have to mention a couple of things about this to make it clear. You could imagine that one of the lines of code that you call is arrays.sort, and you could think of that as being one line of code. Well, that's not the right way of thinking about it, because arrays.sort itself has lines of code. So you have to count all of the lines of code that are in, you know, look at all the lines of code that are in arrays.sort. So it's kind of the extended, all of the lines of code that end up being executed. Now, there are a few exceptions to what I'm describing here. There are some cases where Java kind of, instead of doing stuff with code, they do it, they ask the operating system, there's a bulk copy operation that it asks the operating system to do. So there are a few lines of code where you kind of have to, you know, maybe not take just count the line of code as one, but to count it as some multiplier. But there's another one, there's one that you have seen, that I wanted to mention, a kind of an exception to this. It was an interesting case. I used to teach at the University of Arizona, and I remember that we had a course like this, a second course, that was using a C++ textbook. So what had happened is that at some point in time, excuse me, not C++. The course had been in C++, and we switched it to Java. And what a lot of authors did is they took their C++ textbooks and translated them very directly into Java. And it didn't always work well. So I remember the instructor of this second course coming to me and saying, there's a weird thing going on. The textbook talks about slow sorting algorithms and fast sorting algorithms. And the fast sorting algorithm is running more slowly than the slow sorting algorithms. How is that possible? Well, it's because this person had translated their C++ textbook into Java and hadn't taken into account a particular thing that Java does that C++ does not do. It has to do with arrays. So if you had something like an integer array called list that you set to be a new integer array, say, that was n long, well, that's one line of code. So in my model, we would give this a count of 1. And in C++, this actually executes very quickly. You know, even though it's asking potentially for a big chunk of memory, the computer's pretty efficient about being able to allocate a big chunk of memory to you. So that isn't the thing that slows this down. What slows this thing down is, remember what happens, what Java does when you allocate an array. It auto-initializes all of the elements to the 0 equivalent of the type. It fills it in with zeros. And there are n of those things to be filled in with 0. So this line of code actually has a multiplier of n. So there are a few cases like that where you have to be careful with the model that I've mentioned. But for the most part, it's actually correct. It's kind of a good model to follow. So I'll show you that in a minute. We're going to look at an actual algorithm. I wanted to mention one more thing before we do that. which is that there's a notion of complexity classes that we kind of, as computer scientists, we kind of like to divide up the universe of algorithms into, say, one little chunk of algorithms here, another chunk of algorithms here, another chunk of algorithms here, and here, and here. How many of these did I want to have? I wanted to have that, and I think that's how many I wanted to have. So let's take a look. So I mentioned that, and I don't want to put that one there, I want to put that one here. I mentioned that there's this algorithm called linear search, which is what index of is doing, and I mentioned that that's an O of n algorithm. There are other O of n algorithms, so we kind of would group them all together, think of them as a class of algorithms that have the same kind of growth rate to their time, if we're thinking about predicting the time. We are going to see an improved search algorithm known as binary search. So this is going to be something we talk about in a later lecture. And it has O of log n behavior. So it's faster. The growth rate for it would be related to the log rather than being related to n itself. We are going to see some classic sorting algorithms that are the kinds of sorting algorithms that people use if you just give them, say, a pile of folders and say sort these alphabetically. The algorithms that people tend to use are n-squared algorithms. So we're going to talk about those in another lecture, the n-squared sorting algorithms. We're going to talk about some other sorting algorithms that do better. These other sorting algorithms are going to turn out to be O of n log n, O of n times the log of n. Now, we don't like the fact that there's an n in there, but it's better to have n times the log of n than to have n times n. So these are going to be nicer sorting algorithms that have the n log n time instead of the n squared time. You could imagine having n cubed algorithms. I mentioned that we're going to look at one of those today. There are algorithms that are really awful that would take exponential time, say O of 2 to the n, where every time you add 1 to n, it doubles the amount of time that's required. And there's infinitely many of these complexity classes. So I'm showing you only some of the most common ones here. Now, we talked last time about insert front of linked list. That inserting something at the front of a linked list. So suppose you have 10 things in the list, and we did an insert. Suppose we had 10 million things in the list, and we did an insert at the front. Is the time going to change, if you have 10 versus 10 million? And the answer is no. We talked about inserting at the front. We can always very quickly construct a new node, rearrange the links, and now it's at the front of the list. So this is something that doesn't depend upon the n. We would say it's a constant time operation. And what we do for that is we call that an O of 1. So, we don't care about multipliers, we pay attention to the dominant term. Here, there is no relationship to n, so we would just call it O of 1. In the textbook, my co-author, Marty Stepp, showed a little table of kind of the growth rate for a lot of these different algorithms. The O of 2 to the n you can see is particularly crazy. A lot of these numbers are beyond the age of the universe. So it really kind of shows you how this thing can change a lot depending upon the big O. All right. I want to do an example with you. And this is an example, it's kind of a fun example, I think. A lot of companies have used this. Microsoft seemed to really like using this one as an interview question that they would ask people. So you could call it the max sum problem. So the idea is that you have some non-empty array of values. If it was empty, then kind of the max sum problem isn't defined. But actually, I should have thrown in max subsequence sum. So the idea would be that I want to kind of identify, so I've got an array of numbers, and I want to identify a starting index and a stopping index. And so I kind of want to, come up with a start and a stop, where if you add up everything in the array from here through here, so, going from start through stop, so inclusive. So you add up all of those different things, that gives you a sum, and we want to find the values of start and stop that give you the largest sum. So it's a subsequence because it's not necessarily the whole thing. It's a start through a stop. But it has to be a contiguous sequence like that. You can't exclude anything from the middle. So we're not just kind of trying to pick out, a set of things that aren't all together. So it's got to be a subsequence in that sense. Got to be, a whole bunch of things from a start to a stop that add up to the largest sum. If you were in an interview and you said, well, that would just be the whole thing, you just put start at 0 and stop at the length minus 1, because you're always going to get a bigger sum if you add more things in, right? It's always bigger. I hope some of you are kind of shaking your head and saying, no, that's not true. Why is that not true? So normally with an audience, I ask, and people can point out, it's because there might be negative numbers. So because there might be negatives in the array, it's not necessarily going to be the whole array. I think if you gave that answer that it would always be the whole thing, probably the interview would be over. I don't know. Maybe anyway, who knows? But I want you guys to try to do this problem yourself. So I usually challenge the class that I want to see how fast you can do this. Because people are pretty good at solving a problem like this too. I'm going to show you a sequence of numbers, and I want someone to give me a start and a stop that seems to give the maximum sum. So that's the challenge. Get ready, get set, take a look. And usually I succeed at tricking people when I do this, that I get somebody who points out that this looks pretty good. This is a sum of 22. That is a pretty good answer if you were looking for the maximum subsequence here. But it turns out that's the wrong answer. I kind of trick people in general. If you guys came up with this answer, you're in good company, because I usually get lots of people to make that mistake. The thing is, you have to look really carefully and think through. You have to be a little more thorough. What you'll find out is that if you take all of these values here, 3 through 9, if that's your kind of start and stop, you get a better sum. Because this is 4 and 6 is 10, and 10 is 20, and then there is a negative, but 20 plus negative 18 is 2, and then with 5 gives you 7, with 5 gives you 12, and 12 plus 11 is 23. So that's the maximum subsequence here, is 3 through 9. So it's a little trickier than what you might imagine. So how do we figure this out? Well, let's think about a brute force way of doing it. So you could basically say, for all possible values of start, what we're going to do is, for all possible values of stop, what we're going to do is add them up, some kind of a loop that would add them up, and update max. So that's going to be, our pseudocode description of our general approach. Is we're going to do it in a brute force way. We're going to have a loop that considers all possible starting positions, and inside of that it'll be a loop that considers all possible stopping positions given that starting position. And then there's going to be a loop that adds up the numbers from start to stop. And then it sees whether that's a better max. I said that this is going to be for a non-empty array. So the way that I'm going to initialize is that I'm going to assume that it's 0 through 0. So I kind of set start and stop to 0 through 0 as my initial thing. And then for the various starting values, start could be anything from 0 to length minus 1, so it's standard traversal loop. Now for the stopping values, stop could have the same value of start. What would it mean for stop and start to be equal to each other? Well, that means that it's just one value. Like if start is 8 and stop is 8, then that's the value at index 8. And that might be the answer, actually. Like if you had an array of all negatives, then whichever negative was the least negative would be the maximum sum. I mean, it would be a negative, but it still would be a better sum than you get with the others. So start and stop might be equal to each other. So stop could be as small as start, and it could be as high as length minus 1. So all possible starts, all possible stops. And then we just do our standard cumulative sum. Starting a sum at 0, go from start to stop, adding things up, and if it's better than our max, we update. So this is kind of a brute force approach to this. You know, again, if you're not doing premature optimization, this works. This will do kind of the right thing. Well, what if I wanted to use my rule of thumb, my model, that I'd want to kind of think of how many times are these various lines of code executed. This gets executed once, this gets executed once, this gets executed once. This for loop gets executed once. Now, it's got stuff inside of it, but we only kind of hit the for loop once, you know, and then we have it set up a variable called start, and it's going to do start less than list.length and so forth. But this for loop is inside of this for loop. So what's going to end up happening? This for loop executes its body n different times if n is the number of things that are in the array, because it does the full array from 0 to length minus 1. So this for loop gets executed n times because the outer loop is going to kind of go around and around and around n different times. So this for loop is executed n different times. N different times, we're going to set up a variable stop that we initialize to start and then execute its body. Well, what about the lines of code inside of this for loop? How often are they executed? Well, it's a little trickier because this doesn't start at 0. This starts at start. And it goes less than list.length. So sometimes this is a small number of things, you know, when start is a big number. Sometimes it's the whole array, you know, if start is 0. So it kind of, you know, changes depending upon how big start is. But on average, this loop is going to do about half. So on average, these lines of code inside this for loop gets executed n over 2 times. So this line of code is executed n over 2 times as that for loop executes. Same with this for loop and the same with this if. But remember that this for loop itself gets executed n times. So n different times we execute the body of this loop, which averages n over 2 times. So these different lines of code, n squared over 2. This line of code setting the sum, this for loop, and this if, they get executed n squared over 2 times. Because the outer loop executes n different times, and the inner loop executes n over 2 times. So we get a multiplying effect here. You know, these lines of code get executed n squared over 2 times. But I think you can see, look, there's yet another loop here. Well, how often is this line of code executed? So it's, you know, it has a loop again that goes from start to stop. This executes on average n over 2 times. And if the for loop that is controlling that line of code executes n squared over 2 times, and the body gets, you know, includes an extra multiplier of n over 2, this line of code, this is the charcoal black line of code, and it gets executed n cubed over 4 times. So we have a multiplier of n over 2 because that's how many times on average the body of this loop gets executed. So n cubed over 4, we don't care about the over 4. What we care about is the n cubed, and we would say this is an O of n cubed operation. That would be my prediction, is that I basically, you know, am using a counting type argument to say that this gets executed n cubed times. We're doing kind of an introduction to this today. As I said, there's not going to be an exam question. We have limited time to spend on this. So if it's not entirely clear to you why this would happen or why we kind of do the multiplying in this way, it's okay that you think that. But I mean that you're a little bit confused. But think about what happens when you have a for loop inside a for loop inside a for loop. this gets executed a certain number of times. The body of this for loop gets executed a certain number of times every time this for loop is executed once. But this for loop is executed multiple times because it's the body of another for loop. And then this for loop gets executed multiple times because it's the body of this one's for loop. So we tend to have this multiplicative effect when we have nested loops. So this one ends up, so this is an n cubed algorithm. That would be my prediction. How could we do better? I mean, I think that if you were doing an interview at Microsoft or something, they're not going to be overly impressed that you've come up with an n cubed algorithm, but I think what they would care about most is that you'd be able to do this kind of an analysis and know that it's an n cubed algorithm and know that that's the bottleneck, the sum plus equals list of I. So adding up all these numbers is the thing that's taking a particularly long amount of time. So now we're not talking about premature optimization, we're talking about optimization after we have a working version. How could we improve on what we're doing here? Well, if you think about what's going on with start and stop, you could think of all the different values. Initially start is 0 and stop is 0. There's tons of different possibilities that we consider. Let's think about something that's somewhat in the middle. So suppose start has gotten up to 25 and stop has gotten up to 1,005, let's say. So, your two outer loops are dealing with a start of 25 and a stop of 1,005. What does the inner loop do? The inner loop runs from 25 to 1,005, adding up all the numbers. Then what ends up happening? Then we come back around and we change the value of stop. And suppose that this, there's a lot more left in this array. Then it's going to do 25 through 1,006. Well, what's that going to do? The inner loop does a sum starting at array sub 25, adding it all the way up to array sub 1,006. But why do that? Why start all the way back at 25 and add up all of these things? Isn't the sum from 25 to 1,006 very similar to the sum from 25 to 1,005? I mean, they're identical, other than the fact that the sum up to 1,006 has one extra thing in it. So the way that we could improve this is by getting rid of the inner loop. We start our sum at 0 whenever we have a new start. And then inside of this loop, we only need to add in the next stop. So like if we're going from 1,005 to 1,006, we add in the value at 1,006. That's kind of what we need to do. And we're going to do our updating of the max. Well, so let's do our analysis of this one. So this outer for loop gets executed once, and it executes the int sum n different times, because this outer loop is the standard for loop that does the whole array, 0 to the list length minus 1. So this line of code gets executed n times, and this line of code gets executed n times. Well, what about inside of here? Well, this was the thing that goes from start to the end, and I was making the argument that on average executes n over 2 times. So this line of code right here and this if, they get executed n over 2 times every time we execute this for loop, but this for loop gets executed n times. So there's this extra multiplier of n. So this line of code, they get executed n squared over 2 times. Again, we don't care about the over 2. We care about the n squared, and we would predict that this is an O of n squared algorithm. So that's, and I think a lot of people would be able to figure out that improvement, to get to the n squared. Can you do even better is kind of the next question. And the answer is yes. There's a famous algorithm known as Cadanes Algorithm. And this is kind of the idea that, I have actually a slide for this. We can work with this. So what you do in the other algorithm is you ask the following question. What is the highest sum that you can achieve that ends with a certain value? So for example, initially you'd say, what's the highest thing that ends with 0? Well, there's only one subsequence that ends in 0, and that's the one that goes from 0 to 0. So the best we could do here is to get a sum of 14. Well, what if the subsequence is going to end with element 1? What if stop is going to be 1? What's the highest sum you can achieve? Well, I think you guys can see that it's beneficial to include what came before. If the highest we can achieve ending in 0 is 14, then the best we can do ending in 1 is to include that previous thing, and we get a sum of 22. How about for something ending in 2? Something ending in index 2. Stop is going to be 2. What's the best that we can do? Well, if we include, if we go all the way, from the beginning, if we include the sum that added up to a 22, and now we throw in the negative 23, the best we can do is to have a negative 1. Now, negative is not good, but that's still better than negative 23, for example. Now, this is where a key decision occurs. So if I say, what's the best you can do to form a sequence that ends with 3? So the stopping value is going to be 3. You could include what came before, but the best you can get with including what came before is a sum of negative 1. And that would then give you an overall sum of 3. Well, rather than including what came before, it's better to just start all over again and say that the best sum we can achieve here is a sum of 4. It's not helpful to include what came before, because the best you can do by including things that end in index 2 is to achieve a sum of -1. And it's not helpful to include. That lowers our possible sum. So we say that the best is to have start and stop both be 3. Start all over again. Here the best we can do is a 10. Here the best we can do is a 20. And here we say, well, what's the best that we could do? Again, it's helpful to include that what came before. This gives you a 2. This is the other kind of key decision point to think about what's going on here, is that we basically say, look, the one that's just before this is a negative 18, but we know we can achieve a sum of 2. There's a way of achieving a sum of 2, and 2 is helpful to us. So we basically say, oh, well, then we do want to include what came before, and that would give us a sum of 7. Here that would give us a sum of 12. And here that would give us the sum of 23. So by making one pass through this, we can figure that out. So we have a single for loop. What the single for loop is doing is saying if the sum of what came before is a negative number, we don't want to include it. We want to reset start. And otherwise we do include it. So it's a single for loop. And basically this line of code and this line of code are executed n times, because it's just a standard for loop that runs n times. This is O of n, is what we would predict. Well, let me switch back to the computer. I got just a few minutes to run this for you. But so let me bring up the laptop. And as I said, I've got a program here, and I'll post it to the calendar today so that you can run it yourself if you're interested. Let's run it. I'm going to ask it to work with 1,500 numbers using algorithm 1. Algorithm 1 is the n cubed. So what did we predict? We predicted that doubling would lead to an increase of a factor of 8, and that tripling would be a factor of 27. So 8 and 27 were the two predictions that I made based on my model for the big O. 8 and 27 were what I predicted. I got 7.8 and 26.1. Pretty good. Pretty close to the 8 and the 27 that I predicted. Let me run it again. This time I'll use 30,000 numbers, and I'm going to use algorithm 2, which was the n squared algorithm. And so our prediction, remember the little table, that doubling for an n squared will take 4 times as long, and tripling for an n squared will take 9 times as long. So I'm predicting ratios of 4 and 9 in terms of the increase. 4 and 9 were what I predicted based on the big O. The final one, this final one is so fast that I almost can't time it. I'm going to give it 50, 1, 2, 3, 1, 2, 3. That's 50 million numbers for algorithm 3. So my prediction is that doubling will take twice as long, tripling will take 3 times as long, because it's linear. So I'm predicting that the ratios are going to be 2 and 3. And we get pretty close to 2 and 3. You might find it interesting that for this 50 million list, if I ran algorithm 2 on the 50 million list, it would take around 8 days to run the algorithm. And if I ran it on the n-cubed algorithm, it would take over 200,000 years to complete. So the key thing, though, don't put the pilot on a diet. The thing to worry about is to have an algorithm with a better big O. That's kind of the efficiency that we care about. That's kind of the moral of the story from today. And we'll do more next time.